This gets us into the elementary rules of probability. So I guess I first preface by saying that we're going to use this Venn diagram, or this type of diagram here, to explain and I guess to show the relationship between different probabilities. Okay, so this square, not the yellow square but the blue square, represents total probability. That's always going to be equal to 1. And then the circle represents the probability of event A. Okay? And then in this case, the area around it, which we would call A complement, is the probability of A complement, which A complement is defined as 1 minus probability of A. So A complement is just saying not A. So we have an event that occurs right here in this space, and that's the probability, or that's A, that's the event A, and this circle represents the area, or the amount of probability that it takes up. The box around it is all of the total probability, and so all of the space that is not within that circle is considered A complement, or 1 minus the probability of A. And like I said, we're going to run through lots of examples to reinforce these concepts. And that brings us to the next part, the union, intersection, and mutually exclusive. Again, looking at these boxes, so this box right here represents total probability of 1. And we'll go ahead and look at mutually exclusive first, because I think it highlights best. Mutually exclusive is when two events cannot occur at the same time. So one thing that we notice here is there is no overlap between the event A and the event B. They don't touch each other. They don't overlap in any way. So they're said to be mutually exclusive because that means that A and B cannot occur at the same time. So they operate within the same probability space. There's one total probability for all of the sample space outcomes, but of the sample space outcomes, in all of those sample space outcomes, there's an A and B, and A and B can never occur at the same time. That's mutually exclusive. Okay? The intersection of A and B is denoted by this area right here, when A and B cross over, that middle portion, and that is when A and B occur at the same time. Specifically A and B. Okay, so intersection, you're going to hear this word a lot, and this is written as A with this little symbol here. I'm not even sure what that's called, but we would just pronounce it A intersect B, or A and B. Okay, and then the union would just refer to A or B. So that's the word for that. And this would be this right here. That symbol is just the opposite of the one up there. And this is spoken A union B, or A or B. And that's denoted by this picture right here. This is when, for an event, A can occur or B can occur. So, or A and B can occur at the same time. So the occurrence of only A, the occurrence of only, or of A and B, and the occurrence of only B. The addition rule. Okay, so there's two different addition rules, but they'll make some sense here. So there's the addition rule for mutually exclusive, and so we would say the probability of A union B. So us adding together, or the total probability between the two events of when something's mutually exclusive, the probability of A union B is going to be the probability of A plus the probability of B. Seems simple enough. And that's because these probabilities don't touch each other. So that's that. Now, if A and B are not mutually exclusive, then the formula switches a little bit, meaning they're not mutually exclusive, meaning there's overlap. Okay, we could see by this diagram that there's overlap here. So when we're looking at the addition rule for not mutually exclusive events, there's overlap, and then we have to minus off one of those overlaps. Think of this diagram right here and kind of picture A and B, the circles A and B, moving together in order to overlap. So they're moving, picture them like moving toward each other, and then they overlap, and then they form this picture down here. When they form that bottom picture, notice that this portion, the A intersect B portion, there's actually one on top of the other. Okay, so when we are going to be looking at the union, when we are adding the union together, because we've put those two probabilities on top of each other, we've got to chop off one of the intersections. So that's what this term is. So this formula is the exact same thing as the top, except that we're chopping off one of the intersections. Because, like say, if we're looking at A, now we only have to account for this portion of B. Okay, so why don't you guys turn to your worksheet and number 1, and we will go over some of these problems. The following contingency table summarizes the number of students at a college who have a MasterCard or a Visa card. So remember I said contingency tables were going to creep up later on in the semester. Now is the case. So here we go. So find the probability that a randomly selected student has a MasterCard. Okay, so if we want to know the probability of a randomly selected student having a MasterCard, we just need to look for the marginal probabilities. Okay, so this is a contingency table. The marginal probabilities are going to be just at the bottom here and on the side. Or I guess I shouldn't call them probabilities, they're frequencies. So this is a frequency distribution. And then this is the overall total of students. So if we wanted to know the probability that a student has a MasterCard, okay, so we're looking at A, we would write it as the probability of M, or the probability of MasterCard. And that's just going to be equal to the number of students who have a MasterCard over the number of students possible. So the number of students who have a MasterCard, we would look all the way over here, and it is 2,500. You see that? So regardless of whether they have a Visa or not have a Visa, we're just looking at the total. We're just looking at the marginal probability. So we see 2,500. So if we want to find a probability, we'd say 2,500 over 10,000, and that equals 0.25. And then likewise, we want to look at the probability of having a Visa. And we look and we see that it's 4,000. So 4,000 is the total number of students who have a Visa. And that's over 10,000 possible, so 0.4. And now we get into probability that a student has both cards. So that would be the intersection, right? So now these inner pieces are intersection points. So now we want to look, so the probability of having both cards is letter C here. So that's going to be the probability of M and V. And that's equal to the number of students that have both. And we look up here in the contingency table, and we see that the intersection of having a MasterCard and having a Visa is 1,000. So 0.10. And then has a MasterCard or a Visa card. Okay, so that would be the probability of M or V. Sorry about my writing here. It is hard to write on this tablet. So then we would find the probability that somebody has a MasterCard. Actually, we'll go back to our formula. So the addition rule, and we know that these are not mutually exclusive events because we know that they overlap. And we know that they overlap because we know there's an intersection. So we saw in C that they intersected in some capacity, right? So there's 1,000 students that had there's 1,000 students that had both cards. So we know that they're not mutually exclusive. So we know what formula to use. So that would be probability of M plus the probability of V plus the minus the probability of M and V. And we actually already calculated all those numbers. So 0.25 plus 0.40 minus 0.10 is equal to 0.65 minus 0.10, or 0.50. Okay. And then E has neither card. We would look up on the table where does not have a Visa and does not have a MasterCard cross, and we can see that that's 4,500. So this would be does not have either card, so neither card or neither card. The probability of not M and not V, and that's going to be equal to 4,500 over 10,000. Or 0.45. And then lastly, we're going to look at F here. Uh-oh. Let me get this in screen for you. And F is saying has exactly one of two credit cards. So a couple different ways that you could do this. You could, well, let's do it a couple different ways. So we'll say 1 minus the probability that they have both, and then also minus the probability that they have neither. And we have calculated both of those, right? So 0.10 from part C and 0.45 from part E, and that gives us 0.45. Similarly, we could look at the probability, we could look at the frequency table up here of having a MasterCard and not having a Visa, and having a Visa and not having a MasterCard, and then adding those two up. We would add up 3,000 plus 1,500 to get 4,500, and then take that all over 10,000. And then that would also give us 0.45. So that would be another way to do it. So that's us solving for elementary probability on the worksheet. Let that soak in, and we're going to start on conditional probability in the next video. Thanks so much, guys.